continuing on from our first video, let's work on another example. In our first video, we were able to handle 3-digit numbers on pencil and paper with relative ease, so let's just move on to another fairly small example, given that we live in the age of computers, and let's see what we can do by hand, computing the GCD of two 4-digit numbers, in particular 2,868 and 1,928. So take a minute, give a try to the techniques that we introduced in the first video, using factor trees, divisibility tests, writing out lists of maybe obvious divisors, and see what you can come up with in terms of computing the GCD of these two values. Take a moment, pause, really try it, and then come back. After giving it a try, you should find that all of those techniques don't work very well at all for handling even this relatively small example. And those methods were all we talked about. And so you have to start thinking. GCDs have been very important and have been studied by mathematicians for a long time. And mathematicians were able to compute GCDs relatively quickly without technology. And so if all the methods we discussed before don't work very well, there's got to be something that does. And it doesn't have anything to do really with the definition of the GCD that we've been discussing, the way in which our previous methods do. So it feels a lot more like a trick, and what that method is the Euclidean algorithm, the second half of the title of these slides. So what I'd like to do in the next slide is give an example of just how that Euclidean algorithm works, and a task for later videos will be to describe why that Euclidean algorithm works, since it's not immediately clear that it should. So in order to do this, we're going to start with attempting to compute the GCD of our two numbers. It's going to give us two numbers, a larger number and a smaller number. Let's use the quotient remainder theorem to help us understand the relationship between these two numbers. So starting out with the larger number as an A value, in this case 2,868, let's write it as QB plus R, where B is the smaller of these two numbers, 1,928 in this example, and the Q and the R are from the quotient remainder theorem, also called the division algorithm. When we go ahead and do that computation, which is real straightforward, we find a Q value of 1 and an R value of 940. What the Euclidean algorithm is going to have us do is repeat this process of using two numbers and the quotient remainder theorem until it terminates somehow. So let's keep going. Let's just use the quotient remainder theorem again with an A value of 1,928 and a B value of 940. Again, real straightforward computation. You'll find the Q in this case is 2 and the R in this case is 48. And let's repeat again, this time with an A value of 940 and a B value of 48. Little division tells us here that the Q value ought to be 19 and the R value is 28. And we repeat once more, this time with an A value of 48 and a B value of 28. Q is found very quickly to be a 1, R value is found real quickly to be a 20, and repeat again with an A value of 28 and a B value of 20. Our Q value is 1, our R value is 8, and we repeat one more time. A value of 20, B value of 8, write 20 as 2 times 8 plus 4 left over. And we repeat one more time with A being 8, B being 4, A is 2 times 4, and this time there's nothing left over. And it's this stage right here that's telling us to stop. So let me go back now and explain how the Euclidean algorithm works with a little bit of color. So this time I've color-coded everything at each stage, and then we're going to talk about flowing from one stage to the next stage and about why this is the place where we stopped. So adding these colors, we started by taking an A value, which was our larger of the two GCD numbers, and writing it as QB plus R, where B was the smaller of these two numbers. So we started with an A and a B. We obtained a Q and an R from the quotient remainder theorem. For the Euclidean algorithm, interestingly, the Q value is not of very much importance. It's the R value that's fundamentally more important, because when we move to the next stage, our new A value will be the B value from the previous stage, and the new B value in this second stage will be the R value from the stage before it. Notice that this B was chosen to be smaller than this A. So when we move from the first step to the second step, the starting number that has to be the larger of these two is smaller than it was before. That's something that gives us hope. If the A value, which is the biggest of all the numbers, is getting smaller from stage to stage, there's hope that eventually we'll run out and hit a floor value. So just to make more concise the process that we're seeing with these colors, in the first stage, we start with our A and B coming from the GCD we're trying to compute, and we determine the Q and the R value. Once we have those four numbers, the Q just gets thrown away. And when we move from the first stage to the next stage, or more importantly, one stage to the next, what was the B value is going to become the new A value. What was the R value is going to become the new B value. We then use the quotient remainder theorem to find the new Q and the new R. Moving down from this stage to the next, R becomes B becomes A and Q go away. And we do this until we can't proceed any further. Notice that we stopped here because our remainder value was 0. If we were to try to advance one more stage, B value would become A value, so B equals 4 would move down and be the new A value, but we would have to try to take that remainder and make it the B value. In other words, we'd be trying to divide by 0, and we all know that that's a cardinal sin. So we know that we're done with the Euclidean algorithm as soon as we get a remainder value of 0. And then the magic is that the remainder from the step before, or in other words, our B value at this stage where we get a 0, that's the GCD of the two numbers in question. So for this example, the GCD of 2,868 and 1,928, that value is 4, and it was found through a relatively painless and short process of just doing divisions and remainders, divisions and remainders. We'll discuss why this process works to give us the GCD of our original two numbers in future videos, but the last thing that I want to show you is a really cool way to visualize what you're doing when you're doing the Euclidean algorithm. It's a tiling kind of problem. So one way that I've seen this Euclidean algorithm presented is, suppose you'd like to find the GCD of two numbers. And in this example, I've used 273 and 399 as my two examples. Suppose I wanted to find the GCD of these two numbers. I'm looking for a divisor of both numbers, and I'm looking for the largest divisor of both numbers. It's kind of like imagining I have some sort of room. Maybe it's 273 feet by 399 feet, and I want to tile that room with whole tiles. I don't want to have to get out a tile cutter and break tiles in half in order to tile this room. But I don't want to use penny tile, just super, super tiny and might take a million years to tile the room really nicely. I want to use as big a tile as is possible, but where I won't have to use partial tiles. What I could do to figure out how this is working, to visualize the quotient remainder theorem, I'm taking 399 and writing it as one copy of 273. I could use this one big 273 by 273 tile, and it would take up this much space of the 399, but there would be some room left over. And one of these 273 tiles, when I subtract that from the 399, gives me a remainder of 126. And so the problem of tiling this whole room is analogous to trying to tile this other rectangular room, which is 273 by 126. Can I find a tile that would work for that smaller room? If it would work there, it would work everywhere. So I repeat the process with 273 and 126, saying, okay, a 126 tile won't work. I'd use 2 of those 126 tiles, and then I would have 21 left over. But by the time I get to this 21 by 126 smaller room, the 21 tiles will work. And so I tile that little rectangular room with 21 by 21 tiles. I do the same for all of this space and this space and this space, and then my whole big room would be tiled with 21-foot tiles. So that's a good visualization of the iterative way in which this Euclidean algorithm works.